Alright, someone made a request for me to see P versus NP, and so, yeah, today I'm just going to show over what P versus NP is. So, what P versus NP is, it's from the Millennium Prize problems. So, Millennium Prize problems are math riddles and are really, really, really hard to solve. And if someone came up to solve it, they would get $1 million. But don't get your hope too high because they're really hard. They're really, really hard riddles. And today we're just going to see one of them. And you'll see why it's really hard. So, yeah, P versus NP. We're going to start with P. Now, P stands for polynomial time. Now, polynomial, it's a word in Latin. So, poly means multiple, and nomial means names. So, many names time. Now, this won't tell you a lot. This won't tell you much. But what P is, a P problem, means it's a problem with a solution that is easy to find. For example, 2 plus 2 equal 4. If I told you guys, yeah, 2 plus 2 equals 4, well, you'd agree with me, right? 2 plus 2 equals 4. It's obvious. It's an obvious answer. It's an obvious answer that is easy to find. So I'm just going to write it down. So easy to find the solution, right? Important, right? It's important to know a P problem is a problem that is easy to find the solution. All right. I hope this made sense. Now we'll just move on to the NP problem. So what is a NP problem? NP stands for non-deterministic polynomial time. Now again, this won't tell you a lot, this won't tell you much, but what the NP problem is, it's a problem that is hard to find the answer, but it's easy to verify the answer. So I'm just going to write it down. So it's hard to find the solution. However, it's easy to verify. Verify. Right. NP problem that is hard to find, easy to verify. Got it? All right. Just show an example of a NP problem. So if I told you guys, yeah, this is the solution of this Sudoku puzzle, would you believe me at first? I mean, is it really the solution of the Sudoku puzzle? We'd have to verify to find out. And if we did verify it, we'd know that it's actually the correct answer. It's the correct solution of this Sudoku puzzle, right? This is a NP problem because I told you guys, yeah, this is the solution of this. You didn't know at first that it was the solution, and you had to verify to know that it was the solution, which is why it's NP. It's hard to find the solution, but easy to verify. I'm just going to explain it in a drawing. So let's say we're just going to split that in two. So let's say we have a small circle and then we have a big circle. The small circle is a P problem and the big circle is NP problem. Now the 2 plus 2 would be here, and the Sudoku would be here. Okay, now in this drawing here, a P problem is a NP problem because it's inside the NP circle, and which is why 2 plus 2 equals 4. We can also verify it, which means that it's also NP because we both know that it's the solution, it's easy to find, and it's easy to verify in P problems. However, in NP problems are not P problems because they're not easy to find, but they're easy to verify, right? Now, the big open question now, does P equals NP? This is whether all problems that are easy to check, which is NP, have answers, have answers that are easy to find. So it's going to look like this. So both P and NP are both this circle, and 2 plus 2 equals 4, and the Sudoku would be both in this circle. And so if NP problems have an easy solution, we don't know if it has an easy solution, but if it has, then that would mean that P equals NP. Another way to think of it is, okay, let's say a Rubik's Cube, right? So a Rubik's Cube, there's multiple ways to solve a Rubik's Cube. But what is the best way to solve a Rubik's Cube? That is the question. We don't know yet the best way to solve a Rubik's Cube, which is why we don't know, which is hard to prove that P equals NP. So yeah, I hope this made sense for P and NP. Now we're going to move to NP complete and NP hard. Now these two, okay, we're going to be a little this is going to be a little complicated. So NP complete and NP hard are sets of problems defined by their relationship to problems in NP. So because sometimes, let's say we have problem 1, right? If we find the solution to problem 1, this could also lead to the solution of another problem. We would call problem 2. And yeah, sometimes solutions to one problem allow solutions to other problems. And if we convert one problem into another quickly, a solution to the second problem will give a solution to the first. So yeah, for NP hard, right? NP hard. We say that a problem let's call we'll just call it Bob, all right? The problem is called Bob, okay? We have Bob here, and we say that Bob is NP hard, if every problem, so I'm just going this is NP, every problem, let's say that each circle is a problem, so every problem in NP can be converted into Bob, a NP hard. So a NP hard problem is a problem that it's a NP problem where every NP problem can be converted into Bob, NP hard. This is really complicated, so which means that NP hard problems are at least as hard as every NP problems, if not harder than than all NP problems, because a NP hard question, it could be any NP problem. So that was NP hard. Now we'll just move on to NP complete. Now NP complete, if, right, we take Bob, right? Bob is a NP hard. A NP complete problem is both NP and NP hard. So, which means that if we know the solution to a NP complete solution, we know how to solve every NP problem. We know how to find every solution to NP NP problems, because in particular, because a fast solution to a NP complete problem would imply fast solutions to all NP problems. And therefore imply that P equals NP. Since it is believed that P probably does not equal NP, it is also believed that fast solutions to NP complete problems do not exist, right? So NP complete problems, it's really hard to find a solution to NP complete problems. So I'm just going to make a drawing. So if we draw with NP hard, NP complete, P and NP, it's going to look something like this. So we have a circle, and then we have there, and then it's going to look like this. So P does not equal NP. It's going to look like this. So we have P there, we have NP there. This would be NPC, NP complete. Don't be mistaken with NPC. And we have NP hard there. So NPC problems we know that NPC problems are not P problems. However, we're just trying to figure out if P problems are NP problems, and it's just hard to prove. Now, if P did equal NP, it's going to look something like this. So have like this. Wait, no, that's not pretty. Just going to, so P equals NP, and NP, oh, NP C. And then we have NP hard there. So yeah, this is how it would look if P did equal NP. I hope this was of help to you guys. I know this was out of my reach of expertise. I'm not the best guy in this type of things, but I hope you understood something. I mean, at least something. And yeah, later.